Now, this is a machine that was built and that demonstrates, well, this is not a machine, this is just the schematics, but it demonstrates that if you drop something, do you see the distance when this is just dropped when at the same time? So this will drop here, and do you see that the vertical distances, velocities, and acceleration will be the same for something you drop? So the only difference will be in this case, because you have a spring here, it will blow this thing, it will apply a force here, it will have the continuous Vx, the same one. So basically there's two motions, and both motions are, we can take them as separate things, as separate motions, and we can analyze them separately. And of course we have the equations. The final distance will be BO, the velocity in x times the time. We already said that, how to get it. If you get the first equation plus 1/2 of a t squared, well, that gets cancelled. That's why we only are left with this. And the yf, the distance in final distance in y, again, the first term for the first equation, the first term goes to 0 because we start in 0 here, right? Or here is the same thing. So we get 1/2 of g. We substitute instead of acceleration, we substitute gravity, t to the square. Now there's this thing, horizontal throw. So we can see that BFX, like all velocities are the same as the initial one, and the final velocity is equal just to gt, meaning the acceleration times time. This comes from the second equation. And there is this table that shows us that here's the horizontal motion. Distance in x is initial velocity in x times time, and final velocity is the same as the initial. That's all there is, nothing else. Vertical motion, we have final velocity in y equals to gt, which is gravity times time, and the distance is going to be just 1/2 of gt squared, because we cancel the first term because we start with the initial velocity of 0, and velocity to the square, this comes from the third equation. The final velocity to the square equals to 2 times g, which is the gravity, acceleration going down, times the distance. Again, the first term, the VOY square, gets cancelled. So this is like a summary of solutions. Again, don't forget the VR, which is the, like at the end, remember, here we said that we have this VR, or the resultant velocity is going to be BFY, the final velocity in y, the final velocity in x squared, added and square rooted, which is Pythagoras, right? And there's some websites that you can go and find. There they are. And of course, for the angle, it will be the inverse tangent of the final velocity in y divided by the final velocity in x. We already know that from the first portion. So let's go to this parabolic throw. This is what we saw. If you see the ski guy here, there, we have just half of the parabolic throw. This was to understand how it works. So basically, when you get at a full analysis, like the skier went from here to here, right? Like that, from here to here. So this is the full throw, or the parabolic throw, the full parabolic throw. It will be very interesting. The things that we can get from here is like this angle here. Do you see? It's going to be the same angle here because it's symmetrical. This velocity here going up is going to be the same one going down here at the same point at the same level. This vector and is going to be the same one as this, and in x this VOX is going to be the same all over. Now the only difference between, well, one more thing, that is velocity in y here is 0. Now the only difference between a parabolic throw and something that you just throw upwards, you see, is that the angle here is 90 degrees. This angle is 90 degrees. So basically we have the same thing. We calculate this the same way, and you have the same behavior of the projectile. Here's more info on it. Same thing, right? You can just stop it and read that. So but it says the same thing. Now kinetic equations, we already saw them. Resultant real motion, we have the VR. That's it. And well, just remember that to get the components of in x and in y, we have VO, cosine of the angle, right? For x we have cosine. If we start from the positive x-axis, same thing with this, the angle starts from there and is BOY. So presentation by your teacher, Mr. Rob. Thank you very much. See you in class. Bye bye.